So the topic we have to talk about for today is Taylor series. Let's see. Oh, what that? Okay, so let me just remind you what the idea is about a Taylor series. Um, so the idea of a Taylor series is that it is a specific type of power series. Okay, so a Taylor series is going to be a specific power series built from a function. So the difference now is that I hand you out a function and you will construct like kind of like the Taylor series associated to that function, produced from a given function. Okay. Uh, the way to think about it is that when we had a function, I did mention like these Taylor polynomials, right? Which are supposed to approximate the function up to a certain degree. Okay. So kind of like the way to think about the Taylor series is that it is a limit of Taylor polynomials. So the Taylor series will be a limit of Taylor polynomials. And the formula for the Taylor series will be okay, so I'm going to write it in full generality where like you kind of like center it at a number which I'm going to call K A. Okay. So I'll call this a Taylor series centered at A. In practice, like most of the examples I'll care about in most of the examples I care about A will be 0. So I'll kind of write that as specifically as a separate case, as you just said, A equals 0 here. And that's sometimes called like the Maclaurin series. But it's just like another name for like the Taylor series for like the specific value because it's kind of like the most used value. So in the case of if A equals 0, if A equals 0, the Taylor series is also known as the Maclaurin series. I think that's how you pronounce it. So the Taylor series is known as the Mac. I, I think it's like that. Let me check actually. How do you type it? Uh, this name. Yeah, this is Maclaurin series. So it must be French, probably. Maclaurin. Mm, Oh, it's a single name. So. But I'll kind of just refer to it as a Taylor series because it's you know it will be the most common case that we'll care about. So the kind of like the first question that you would like to know or like would like to answer is like to what extent is this really like the function you started with? So like the main question is like to what extent is this series literally the same as f of x? Like the idea is that you should think about this because again this is like a limit of Taylor polynomials. And if you remember like the previous discussions we had a couple of classes ago, like the Taylor polynomials in a sense kind of like are better approximations to the function. So like the main question, is to what extent does the Taylor series that is when does Yes. Mhm. Right. It was when exactly. It was when I had like the actually let me see if yeah, I think if I find it on GeoGebra, like I could find it pretty quickly on GeoGebra West. Okay. Like, so yeah, if you go to yeah, it was kind of like this Taylor polynomial, right? Let's see. Oh, this one is cute because you can approximate it about any value. So like it's kind of giving you the approximation. And then let's say, so this is kind of, okay. So the degree zero Taylor polynomial is a constant. The degree one is a linear approximation. That's why you see a line. Degree two is a parabola. Degree three is cubic. Degree four, well, it's quartic, quintic, and then boom, boom, boom. It goes on, and you see like the terms being added and added, right? So kind of like the idea is that at infinity, adding if you kept this process for eternity, like that is like the Taylor series. Now, for something nice like a sine function, it does coincide with its Taylor series always. So that's why like the approximations get better and better. But like um, oops. But yeah, like in general, like not it's not that sort of um pathology that we're interested in, but you can cook up functions where like the Taylor series is not the function. Okay, they do have like weird behavior, so like there is a price to pay. Like kind of like the rule of thumb that you should have in mind is that like the nice functions that you know from calculus 1 and 2, they have like a Taylor series that coincides with the function. I'll kind of like write something a little bit more precise, but so like it seems something in practice that you don't have to worry too much at this point, but like later on it does become a more important issue. Um, yes.
Think that by taking like different derivatives from zero to infinity
Mhm.
with like those other changes to it, should be the best approximation toward both.
Right. It's saying like kind of like a way to put it is like if you give me the value of the function at zero, the first derivative at zero, the second derivative at zero, the third derivative at zero, the fourth derivative at zero, and all of these others, right? Any derivative at zero that you could ask for, which like goes to up to infinity, I could cook up a formula that will recover the function, like, at any value of x, that would give, so, it's kind of like but it's kind of like you have to know everything about the function at zero, right? Like, because that produces these numbers, and then you apply like divide by k factorial times x to the k, and that kind of like gives you the the function. Now there are other ways to, like, if I have some time, I can kind of show you some other ways. Like there are other ways to kind of approximate the function, but in a sense, this is kind of like at least a natural way to do it. If you kind of like start like from the perspective, we're just generalize. This is kind of like a generalization of the tangent line, right? Like because the tangent line uses like the first derivative, and then no one calls it that, but you could call it like the tangent parabola, and then the tangent cubic, the tangent, and then the idea is like this is kind of just a limit of that.
So by knowing the value, like derivative at a specific point, we could like try to estimate the approximate.
Exactly. Yeah. Exactly. Like right, like all the derivatives at a point. Yeah, it's kind of like saying if I know all the derivatives at a point, including the value of the function at that point, then I will reconstruct the entire function. Which is kind of like a crazy thing, but like it does happen basically for the nice functions that you know of, and I'll kind of like write some formulas. Yes.
Is the approximation very exactly a certain function? Does that mean that that exact function, like every part of it, like all the way from like on its entire domain, can be exactly reconstructed using small functions?
Well, right, exactly. So, for example, like actually before like kind of like giving you like a more general answer, let me write three functions for which this is completely true, right? And these are the only three Taylor series that I would say, oh, you do have to know like from heart. Like I wouldn't expect you to know any of the others, but so here are three Taylor series that you should know of. So the first one is the Taylor series for e to the x, which I think I have written before. I'll write it like this, but this is like a super important one. And again, it's always useful when you write a series to kind of like write out the first few terms just to see how it looks. So if you kind of like do n equals 0 and n equals 1 and equals 2, things like that, you get 1 plus x squared over 2 plus x cubed over 6, because like it's like it would be with 3 factorial, right? And 3 factorial is 3 times 2 times 1, so that's where the 6 comes from. Then x to the 4 over 24, right? Plus x to the 5 over 120, etc., etc., etc. So if I'm writing it like this, I do mean that this formula holds for any value of x, any number on the number line. So this formula is correct. This is true for any value. And that's how you can get kind of like cool things that otherwise it would be hard to know. Because, for example, if you take x equals 1, right? So as an example, take x equals 1 in this formula, right? And what do you get? You get e to the 1, which is just e, right? Like the famous number e. Then that would be what? Like 1 to the n is always 1, right? It doesn't matter what power of 1 you put in there. So you would get 1 over n factorial. So that tells you that, like, the way you should think about this is that you get 1 plus 1 plus 1/2 plus 1 6 plus 1 over 24 plus 1 over 120 dot 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 dot. And like, well, I mean, I'm not the best at fractions, but 1 plus 1 is 2. That's great. 1 over 2 is 0.5, right? So at least this is 2.5 already, right? So this is 2.5 plus 1/6 plus 1 over 24, and it continues. Oops, sorry, this should have been 120. And if you have ever plugged E on the calculator, you get like 2.71 something, 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 something. And like you can see pretty quickly that this will get very close to that number that you get in the calculator because a factorial is so big. Like, and you're putting factorials in the denominator. So this, like the terms that you keep adding here very quickly, like they become very, very, very small, very, very, very fast. So this is like a pretty good approximation. I'm sure like if you and here, like you get almost like the first few digits, like that you would get like if you plug it in on the calculator, you see. Um, so that's kind of like, and you could, and I think I had, you get also things that you would not have expected necessarily unless you had like the formula. Like, for example, if you take x equals -1, right? I think I had mentioned also this one before. Then you would get 1 over e, and then now you get like kind of like an alternating series, right? With like 1 over n factorial. So it's like 1 minus 1 plus 1/2 minus 1/6 plus 1 over 24 minus 1 over 120 dot 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 dot. So it kind of keeps flipping back and forth. And then like, okay, these two would cancel. So you get 0.5 minus 1.6 minus 1 over 6 and so on. So which is like, again, like highly non-intuitive, like, that, like getting like these approximations and things like that of that sort. So here's another, now that we're still talking about e to the x, here's like a very, and this is why all this stuff is so useful, because for example, here's another, here's a more interesting perhaps application of this Taylor series stuff. So here's an application. The Taylor series for e to the x. Oh, sorry, yes.
So it was used like approximates.
Yeah, many times, especially for something like the exponential, because the convergence is so good because of this factorial makes things shrink really, really fast. Yeah, it's like a very good approximation for like many functions. And also it's a great tool for integrate, which is actually what I'm about to show, like that is convenient for that. But yeah, like kind of like the way to, I still forgot that I was going to post this YouTube video with applications Taylor series. I'll kind of like post it before the time, just in case someone wants to check it out as motivation or thing. But yeah, no, like definitely like the power series, which is how you could also call this like a power series expansion because you're expanding e to the x in terms of a power series, But yeah, no, definitely it's like for numerical approximations like of this sort, and also for like integration or derivatives usually are easier to find. Finding derivatives is not as bad as finding integrals. Integrals, if you notice, they do require a lot more effort. Like there are tons of integration techniques. Derivatives are kind of like strangely kind of easier for whatever reason. So yeah, like for integration, they are convenient. So for example, here's like an application of it. Okay, so if you look at this integral, I promise you, you will fail if you try to do a substitution, if you try to do integration by parts. You can try to do whatever you have learned so far and you will fail. You will not be able to find like an antiderivative for this function. I mean, you can even show like that you cannot find it like in terms of like the function, like that you cannot find like a formula in terms of things that you would recognize. Okay, so like these like as a direct problem, it will fail, like but here's like a very clever trick if you use a Taylor series, because here's like a way to find it. Well, just to be more specific, I'll say in terms of a power series, in terms of a power series. So we do have like the Taylor expansion for e to the x, right? We already wrote it before. But here's the cool thing, like since this works for any number x, in particular, it works if you think of x as being minus t squared. Like, like there's nothing that said, minus t squared is just some number. So this works for any value of x. So this works for any x. So you can just choose to write x as minus t squared. So let's write. And that gives you like an expansion for e to the minus t squared. So and well, I mean, if you want to write this a little bit better, you can take out the negative as a negative one to the n. So this would become negative one to the n, and t squared to the n is t to the 2n divided by n factorial.
Using the Taylor series that we know.
Right. Like it's kind of like you use a Taylor series. It's kind of like a parasite. You use a Taylor series that you know to find a new Taylor series. You parasitize on the previous formula, so like by a clever substitution, like because by the way, you could totally find it, just find the first derivative, find the second derivative, find all the derivatives and plug in at t equals 0, right? To get like it would give you the same as what you just found. But of course, this is like infinitely faster than trying to find like a formula for the nth derivative of this thing, because it will require even the product rule to find like the nth derivative, because every time you take a derivative, you kind of have to bring down by the chain rule like a factor of 2t or something like that. So you have to start, and then they accumulate, and then you have to apply a product rule. So it's a mess to find it directly. But let me just write as a remark that it will be the same series that you find if you use a Taylor formula directly. So gives the same. Yes.
It's like the Gaussian integral kind of,
Which one?
the Gaussian.
Right. Like actually, that's why I'm writing it as well. Yes. So right, if you were to graph, something like right, if you graphed f of t equals e to the minus t squared, that does give you like this bell curve or like like what people do know like as the Gaussian, right? So like you get something. It's symmetric about the t-axis, and it kind of like looks like this. Like because it's like, I mean, this is 1 over e to the t squared, right? Like that's another way to think about this. Because of like the exponent rules. So you can kind of like see that this gets to 0 really quickly because like the denominator becomes massively large. And at 0 is kind of like big, yeah.
Same or this
Yeah, like it is the same, okay, it is the same normal distribution, except that if you want to use it in statistics, you have to, what they say, normalize it so that it integrates to 1. So that you can interpret it as a probability, that's like a probability that what they call it. But yes, like essentially it's the same. Okay. But it is a very important function, right? And like, so if you have this expansion, what happens with the original integral we were trying to solve? This is what I had asked to find, right? But the idea is that you can just substitute e to the minus t squared with this Taylor expansion or like power series expansion. Like you can call them, you can use either name. And then the nice, and I believe we had talked about that before. The miracle about a power series is that you can integrate term by term. This is like the amazing thing about a power series. So you can kind of like move the integral symbol past the sum, and then you just integrate t to the 2n, which is super easy to do because polynomials are easy to integrate. Like the easiest thing to integrate in the world is a polynomial, like or like a power of x or a power of t. So because of the, I can kind of like write it explicitly just to make it more clear that it's kind of like a switch, like in the order in which they appear. So and then like that is easy to integrate because what is the, oh sorry, t to the 2n, sorry about that. So what is the integral of t to the 2n? You just add 1 to the exponent and divide by the new exponent, and then you're done. So you would get and then you can add like a plus, like an arbitrary constant of integration at the end of the process. Like, so you can like, let's just put it plus c, like an outside, kind of like, I'll put it at the beginning because I don't want it to kind of be thought that it's inside the sum, yes. Sorry, what can you, why can you?
Previous step, why couldn't it be observations?
Oh, like, why can I move these two, you mean? Well, we didn't really go over it because I just mentioned it as a miracle. So like, I mean, no, but like, like the why is not clear for sure. It's just like, it does take some work to prove it more than we have time to prove. Like, you know what I mean? But you definitely need to justify something because it's right. It's not clear why you can just kind of like switch these two. Like, but it's like an article of faith for this course that like you can do this, like, you know, but it can be proved for sure, like, you know, but is that making sense? Like, yeah, like, so same with derivatives. Like, what I said is if you have like a derivative, you can also switch. And that also, like, I didn't explain why it happens, but because it's not too bad, but at the same time, it's not that easy, you know, kind of like, it's kind of like in the hybrid proof, like, yes.
The 5 by 2.
Oh, yeah, excellent. Yes, thank you. Yeah. Woo. 2n plus 1 here, you're saying? I'm glad you caught it. Is that now good? Yes, I think that should be fine. Now it does look good, right? Yeah. Oh,
I was gonna ask why the two.
yes, no, it was just because I forgot it. Yeah, thanks. I I don't know, like, you know, take that for this is like again, like you have to come at it with an approximation perspective. So this is kind of like a good replacement for having like an exact form. I mean, in a sense, it's like an exact formula, but in quotes because it goes on forever, right? So it's not the same as saying sine or square root, like, you know, it's not easily recognizable in terms of something you know. But if you're willing to kind of like stick, you know, with some of the first few terms, that is a decent approximation for what like the actual antiderivative would have been. Again, because like if you think about this function, like it goes to zero super fast, and what that means in a sense is like the convergence, then you know this series will converge to like the function like very quickly, or like to the antiderivative, like, you know. Is that making sense? So yes, so that is and this is like a good example that shows you like kind of like this power of like the Taylor series, and then it's like one of the main reasons why power series are so useful, because it allows you like the problem of taking derivatives or integrals kind of collapses, like it just becomes like term by term, and it does like pretty simple. Yes.
Uh,
Mhm.
Does the result, the resulting series always converge?
Yes, as long as you're working in kind of like the safe zone, because the Taylor series is just like a particular power series. And as long as you're in the, you know, as long as you're in the interval of convergence, then you can integrate term by term, and like it does, like it will have the same radius of convergence and everything, like, you know.
So is this converge to like you or like function?
Well, the way, because it's an antiderivative, like, for example, if I can put bounds here, right? Like if I can put like kind of like an integral from 0 to 1, right? Then you would have evaluated this at 0, 1. You can evaluate each term at 0, 1, and then that would give you like an actual number, right? Here, since I wrote it as an antiderivative, that just what I'm claiming here is that this is a function, right? This is a function whose derivative would have been like, you know, e to the minus t squared. So, but yeah, you should regard it as a function, or like a family of functions, you know, because like an antiderivative is really a bunch, they all differ by a constant. But yeah, like what I'm saying is that these does define like a function of t with the property that its derivative would give you e to the minus t squared. Yeah. But yeah, if I got put like actual bounds, like 0 to 1, then that just means that like first that you don't need a constant of integration because they always go away on a definite integral, and then that just means that you would evaluate at 0 and at 1 each individual term, and then you can like add them all together, because you can do like the separate indefinite integrals. That's kind of like the point. Is that okay? Any other questions about that? Okay, let's move. So as I said, definitely super important to know the Taylor series for e to the x. Then after e to the x, the two other ones which are really important are sine and cosine. They're like nice to have around as well. they're kind of like impaired, come like as a family because sine and cosine are very related. So the Taylor expansion for cosine of x and the Taylor expansion for sine of x is the yes.
I think this expression, like, this expression, is that only valid in the safe zone, or is
It's true, but it's just that sorry, I was going to say add that the safe zone here is also any value of x for sine and cosine. It will converge regardless of the value for x. Like if you remember, like there was this radius of convergence. If you apply the radius of convergence to this power series, it will be infinity. So like there won't be like any convergence issues. Like they are fine. Like so for any value, I will give like next like an example where like there's an actual safe zone, uh, so that you see the difference. But yeah, for these two, like also you can plug in whatever value of x in the world you want, and that will be an agreement. So, um, so. Mhm. Oh yeah, no, like definitely. I'll actually the next one that I'll write, like you'll see what would happen. Yes. Um, Here you can also use any value of x. No, but for example, there's things that you can see here from the Taylor expansion. Like, like for example, in the Taylor expansion for cosine, it's always x to the 2n. 2n is always an even number. So there are only even powers of x that show up here. And that's related to the fact that cosine of x is even, right? So if you remember, cosine of x is equal to cosine of negative x. Yes. Oh, right. Actually, let's, well, I was going to do it with the derivative, right? If you take the derivative of sine, that should be cosine, right? So let's see, if that, you know, what is it like? Yeah, according to this formula, what would be the derivative of sine? It would be the derivative of this thing that I just wrote, right? And kind of like again, like the miracle with the power series is that you can kind of like exchange the order of these two factors of taking the series and the derivative. So you are actually taking the derivative of these individual terms, right? Right, and then kind of what is the rule? Like this comes down, right? So you get. But and if you use the fact that 2n plus 1 factorial is 2n plus 1 times 2n factorial, right? Like there's like a small cancellation that happens here. So you get. And that does that I believe does give you right, like does give you like how I wrote like the cosine Taylor expansion. So you were saying that you were asking me why there's a -1 to the n for sine. Oh, the thing. Okay. Ah, gotcha. The thing is like you do have to play there with the re-indexing Because yeah, like let me see if like let me just say like okay, right, like we can do the integral of cosine because you want to see the integral well the integral of cosine should be well the integral of cosine would be sine, right? Um so like or you're talking about like why if you integrate cosine, why don't you have like a minus overall minus sign in front of well I wrote for sine of x. So okay. So okay, so you want to integrate cosine of x, right? So this would be integrating this series, right? So again, you integrate each term separately, right? Well, you could put the plus c, but in this case, like, like actually you can set it equal to 0, but because you know that sine of 0 equals 0. And then like this does become, you know, right? That doesn't require the negative upside of the Taylor function for sine, right? Uh, or where were you thinking about putting like that? I mean, this is the same as the one that I had for sine of x, right? The thing is like, it is true that the formula for sine of, I mean, because like the integral of cosine is sine, but, yeah, no, maybe if you were thinking about the integral of sine, that should be negative cosine, right? But that will also work if you kind of like play with the symbols because, like maybe that's, if you wanted the integral of sine, that would be the integral. Actually, this is a good example because like sometimes like you can write the Taylor series in different ways which don't look exactly the same, and it's kind of good to understand where the difference is. So let's see if like maybe this is what you're wondering. And then you integrate each term. When you add, you get x to the 2n plus 2, right? Oh, here you do need the constant term actually. So you get x to the 2n plus 2 over 2n plus 2 times 2n plus 1 factorial, right? Now, what's the difference? Like, okay, I do agree that that one doesn't look the way I wrote the series for cosine of x, right? The thing is that you have to count, but the difference y is like kind of like if you take n equals 0 here, right? That means what is the highest power? Where does this start? It starts with x squared, right? Whereas if you kind of like look at the formula for the cosine as I wrote it, right? This starts with like x to the 0, right? So it kind of like the way this one is written kind of like starts with x squared, x to the 4, x to the 6. So it starts kind of like shifted compared to like the version how I wrote it originally. So you do have to do like you do have to kind of like re-index things, which is what you would call that, so that like they kind of like all begin at the same term. But if you kind of start plugging terms, you will see that they do have like the same expansion. So for example, this would be like a constant. So what do you get at n equals 0? So you get -1 to the 0. Right, let's see. Oh, you're saying that this is oh, that's the manual sign that you're wait, let's see. Let's see. well, right, like this would give x squared over 2, but like, yeah, there's a minus here. Oh, no, of course, like yeah, it will give you minus, yeah, like it won't give you like the cosine one, it will give you minus the cosine one, right? Yeah, like I'm sorry, this cannot be compared directly with, yeah, sorry about that. Like I'm talking to myself and I'm sure like what I'm saying doesn't make sense, but like, okay, so you would get c plus x squared over 2, right? What would happen if you take n equals 1, you get negative, right? And then x to the 4th, right? And then 4 factorial, and it continues, right? On the other hand, and again, this is like a constant of integration, which you can, like, you can choose so that it all matches. Sorry, on the other hand, it would have been convenient if I had plugged in some values here for what all of this is. Like you get at n equals 0, you just get 1. So you get 1 minus x squared over 2, right? And that's what you get if you put n equals 1. Then if you put in n equals 2, you get plus x to the 4 over 4 factorial. And it continues, right? And by the way, this one, like just to put it here so that you also have it. If you put n equals 0, you get x. And then you get minus x cubed over 3 factorial plus right, x to the 5 over 5 factorial, and then kind of like that keeps going. But so like I should put it here on the board so that everyone can see it more easily. Right, so the cosine of x, the way it's written is 1 minus x squared over 2 plus x to the 4 over 4 factorial, and then it kind of. And so if you notice here, when I integrated sine, right? When I integrated sine, the integral for sine was a constant plus x squared over 2 minus x to the 4 over 4 factorial. Right, so if you multiply, if you multiply this by -1, you do start matching the coefficients of this one. So like that does tell you that it would be like negative cosine of x, right? So it was, I mean, I'm not sure if I'm answering your question, but yeah, like it does match, like, it doesn't matter whether you integrate sine or cosine or, like, you just have to go chase down things, because the way I wrote, like, it is true, the way I wrote this one, it starts at a power of x squared, and the way I wrote cosine originally starts at x to the 0, but it's just because of this constant of integration that kind of like forces it to match. So yes, like the constant of integration can be useful if you integrate, like because of this antiderivative stuff. Oh, sorry, yes. Yes. More or is that okay or more?
I just missed the cosine x.
Oh, okay. Yes, and like, yes, I was saying, like, regardless of which it is, you can just like integrate term by term, and then that would work like that. Yes.
Right? Constants, yes, like say another constant -1.
Right,
And then that would ignore exactly.
Yeah, so to kind of like make it look more similar, yeah, you can take this C as, right, well, I guess, right, constant -1, and then that kind of like makes it even more apparent that one is minus the other, yeah. Okay, now I do feel I should at least give you an example of this Taylor series, like not being the same as the function, like everywhere, because like I kind of have been like keeping it too hidden for now. So, and we only, so as I was saying, for those who came in late, so for on Monday, I will continue doing examples. Like, so I don't have like any new, I won't kind of cover new topics which are not on the second exam. I already finished all the theory, but I do want to do some more examples, and then I'll kind of like do maybe some more examples for like a couple minutes and like half of the class, so that like the other half, if you want to stay around and ask me questions more specific, you can. But yeah, like the other one that not okay. Here's an example where you do have to be careful with the convergence. So an example where the convergence is tricky, where like or where you have to be aware of the convergence. You have to be aware of convergence issues. So take, for example, a very nice function like what is the graph of that function? Okay, so like the only thing that really matters to remember here is that you know, it has like an asymptote at x equals 1, right? Like a vertical asymptote. So x equals 1 is kind of like a dangerous number. And then here's like the if you have numbers which are slightly bigger than 1, then the denominator is negative, right? So it kind of goes to negative infinity from the right, right? Like if you use slightly bigger numbers. So then it kind of goes like this. And then if you use numbers which are slightly less than 1, this is still positive, but it is getting bigger and bigger. So kind of like the graph. That is roughly the graph of that function, right? Is that okay? And one can check, okay, what is 1 over 1 minus x? If you call x r, it's 1 over 1 minus r. This is like this geometric thing, like it's related to the geometric series. In fact, like one can show, like, you know, like if you start computing like the derivatives and all that stuff, you can find that the Taylor series, you know, after finding derivatives, if you find the derivatives, let me put it like this. If you find the derivatives, the derivatives of fx at 0, you will see that this Taylor series is and again, like which it for this particular function does happen to coincide with the geometric series, right? This is exactly the same as the geometric series. Well, at least if you started at 0, it does give you 1 over 1 minus r. If you started a geometric series at 1, you get r over 1 minus r. But now, what's the interesting thing here? That this, like the left-hand side, you can plug in any value of x besides one, right? For 1/1 minus x. So notice that for you can use any value besides one, evaluate it at any value of x. Whereas the geometric series, we know that the geometric series is only valid when the absolute value of x is less than one, so it's between -1 and 1. Whereas the geometric series is valid as long as x is between -1 and 1. So like, so what that means is that in this formula, you are allowed to plug in any value for x, provided it's between -1 and 1. Like, it's not like you cannot equate the two, because again, like, for example, if you take x equals 2, like, actually, this is like a super extreme example. Like, imagine you thought that this is continue, if this were valid for any value, were always valid, what happens if you take x equals 1? Sorry, take x equals 2. You would get 1/1 minus 2 equals like a sum of positive things, right? 1/1 minus 2 is -1. So you're getting like, you get something completely silly, like -1 equals like a sum of positive quantity. So like that tells you, which this is completely off, terrible, right? So this formula completely breaks down once you start plugging in values outside the domain of the interval of convergence, what we were calling before the interval of convergence. And it kind of makes sense if you kind of go back to the graph, just to go back for a second to the graph of the function, because in a sense, if you think about the graph, what is the purpose of the Taylor series? To approximate the function as best as you can, right? So because like the series is being centered at the origin, right? Like I'm doing the Taylor series center at the origin. So you're trying to approximate the function starting here, right? So like kind of like the Taylor series is doing its best effort, but like you cannot ask too much to it. Like it eventually has to hit what you could call like a singularity, right? Like, and then how can you expect it? If you're trying to approximate it here, how can you expect it to kind of like do a 180 and kind of like continue here without any issues? Like you're asking it too much. So it does make sense that it wouldn't work everywhere. But like this is like a good example where like you have like a series, right? You have a function. The function kind of makes sense everywhere except one, but the series is kind of like more limited, like in scope, because like the singular, like the asymptote kind of like forces it to like fail after a while. Okay. Does that make sense? Kind of like. So since we're almost done with time, but just to continue here with this series, because this is like a super useful series. Um, Still, like the idea is that you can kind of like parasitize on this formula to find other series. So for example, how can you find, so find, here's an example of this. So here's the idea. You can call, I like sometimes to call it the minus minus three. So a plus is a minus minus. Like, so what is 1/1 plus x squared is 1/1 minus minus x squared, right? And then let's think of this as r. Let's think of r as minus x squared. So this is 1/1 minus r, right? And perfect, this is a geometric series for r, right? Like this is like the regular geometric series for r, like the one I just wrote, like, for 1/1 minus x. You just have to think about the letters, right? And so this would be of like r to the n. But what is r? R is negative x. So this would be which if you like, you can write as like, so 1/1 plus x squared equals a series of -1 to the n times x to the 2n. At least for x between -1 and 1, right? For x. Yes. Well, the thing is like, right. R should be, yes. The thing is like, I took R to be the minus x squared, right? So if x is between -1 and 1, its square is kind of like between -1 and 1. So it's not an issue, right? Like, yeah. Otherwise, you have to be more careful with that. But like squaring a number between 0 and 1 keeps it between 0 and 1, right? Like squaring doesn't like, once it's less than 1, it kind of like shrinks it even more. So like you kind of stay in the same, kind of like squeezes it actually into the same zone even more. But yeah, otherwise it's like you have to be keen on that because it could be messed up, like if it had not been exactly 1, right? Because no, but that's a good point. Any other questions? Yes.
If we're given a range to find, series on this, but that's the range of convergence.
I mean, yeah, like it won't
I still
be.
like to translate.
No, like, yeah, or I would ask explicitly find that, or I would just like, write it as find the Taylor series, kind of like that. You do it naively, and then I ask you explicitly what was like the convergence, like the integral convergence, so that you kind of realize, oh, I do have to think about for which values of x this would have worked. Maybe before I'm done with this, at least between x negative less than at least for x between -1 and 1, then you could integrate both sides of the equation. What is that integral of 1/1 plus x squared? arctan, right? So let's integrate. Well, again, like, let me put like a constant of integration. Sorry about that. Integrate both sides. And then magically gives you like a Taylor expansion for like the arctangent, at least between those values. So, and that's kind of like the, that is kind of like the fun part of the Taylor series. Like you can really parasitize on old ones to kind of like construct new ones without having to go through all this titanic effort of like finding all the derivatives, finding a formula for the derivatives. If you have some basic building blocks, you can just construct the others by taking derivatives or integrating like in clever ways or doing substitutions of this form. So it's kind of like a little bit of an art. It's not as like, obvious. Oh, sorry, I forgot a negative one here to the end. It's not like as obvious what to do at first, but like something like this, I would break into steps. I would first be like, find the integral, find the Taylor expansions for 1/1 plus x squared, and then doing an integral or derivative, find like the Taylor expansion for like arctan, so that like it has to be connected somehow to this stuff. But yeah, as I was saying, so on Monday I'll do a few more examples of this sort, and then I'll just kind of like, I mean, if you have anything else to ask me, you can, because I'll just kind of like talk for half the class. But let's finish here, and tomorrow's recitation you'll have more problems of this type when you play around with this stuff. And let me just pause a recording. Yes.
Small thing, would it be -1 to the n plus one or just negative?
Oh no, because if you are just integrating the x,
Yeah.
so this is like a constant. So it's just like the integral of x to the n, is that make or x to the 2n. So you just have to add 1 to the exponent and divide. It's kind of like an illusion. If this had been like 3, you would just leave it as 3, right? It just happens that it is -1 to the n, but it's just like a constant.
Okay, can you break that?
I mean, okay, if I divide Taylor series by another Taylor series, it won't simplify. I mean, then it's like a mess. Like the product is it's better, but like a division is not like a. It's not like a. Like doesn't give you something that you can identify easily as Taylor series. So like division like does fail more like. Does ability of the mechanics, you can just like multiply them, but when you multiply them, like, like the close over time, like multiply them properly. But yeah, like division is like a.
Yeah, I wish like the last one was optional.
Yeah,
It was like
because if you think about it, you're putting like a sum over another, how can you rearrange that as a single sum? But and it's not like an equal problem.
So, now this is the right stuff.
I get that. Now, like, in the department, if I want to talk about like scheduling for.
Because
Cause like I would need the pre-req for schedule.